Welcome to Factoring Beyond the Basics Part 4. For this video, I'm going to assume that you've watched or understand the concepts that were discussed in Parts 1 through 3. In those videos, I discussed factoring expressions that had a greatest common factor, factoring the difference of two squares, and factoring the sum and difference of two cubes. All of those strategies will come back in the problems that we're going to be doing in this video. So let's jump in with expressions with three terms. And you'll notice I didn't say factoring trinomials because although the first few problems that we do will be polynomials, after that we'll work with some expressions that aren't polynomials at all. Remember, polynomials assume that the exponents are whole numbers, and some of the problems that we do will not have whole number exponents. But let's jump in. The first one is a polynomial. The directions say factor completely, and here's the first example. We're going to factor 3x to the 19th plus 7x to the 18th minus 10x to the 17th. As always, we look for the greatest common factor first. There is an x to the 17th in common, so let's take that out. And then we're left with 3x squared plus 7x minus 10. Now at this point we have a trinomial that's quadratic. In previous videos you've seen how to factor quadratic trinomials. I'm going to use trial and error when I factor these. If you use some other strategy, that's totally fine. There are a variety of strategies for factoring three terms. So whatever strategy you've used, feel comfortable using that here too. So I would have a 3x and an x for my first terms. I see I have a 10 or a negative 10 for my last term, so I realize it's 1 times 10 or 2 times 5. And if you roll through the possibilities, 2 and 5 and 2, neither of those work. But what does work is 1 and 10, with the 10 in the parentheses with the 3x and the 1 here, if I put a plus on the 10 and a minus on the 1. And again, I'm not rolling through all of the possibilities showing you that piece. I'm assuming that at this point you understand how to factor quadratic trinomials. So this one is done. Essentially what made this one a little more challenging was just that there was a common factor of x to the 17th, but still not too bad. We'll do some more complex ones here in a few minutes. Let's move on to the next one. It is also a polynomial, and it is x to the 10th plus 8x to the 5th plus 12. We look for a common factor first. I don't see a common factor besides 1, so then we move on. But it is an expression with three terms, although it is not quadratic. But it is what we call quadratic in form, and I'll show you why. If I were to rewrite this problem as x to the 5th squared plus 8x to the 5th plus 12, we would say this is quadratic in x to the 5th. In other words, with respect to x to the 5th. In other words, I could make a substitution. I could say, let u equal x to the 5th. And now I would have u squared plus 8u plus 12 as my expression to be factored. And now I could factor this the way that I normally do. Again, I use trial and error. You use whatever strategy you prefer. So I put in my u and u. Let's see, 12 is 1 times 12, or 2 times 6, or 3 times 4, and 2 times 6 looks good to me, with a plus in both places. But since I made a substitution and made x to the 5th equal to u, I do have to substitute back. The problem was presented with x's. I need to finish with x's. So I'm going to substitute back and put in x to the 5th plus 2 times x to the 5th plus 6. And it's finished. But let me mention this. We don't actually have to put in all these intermediate steps right here. Some people prefer to, and if the problem is fairly complicated, I might prefer to make that substitution. But generally, I prefer not to on a problem like this. So in this particular problem, with the x to the 10th plus 8x to the 5th plus 12, I would just simply set up these sets of parentheses when I recognize it's quadratic in form. And I know it's quadratic in form when this exponent, let me highlight it for you. This exponent right here is double this exponent right here. And notice we don't even have a variable at all sitting right here. So I'm looking at those two exponents and the fact that I don't even have a variable at the end. So I'm going to just write this as x to the 5th. Oops, let's go back to the black pen. X to the 5th and x to the 5th, and factor as I normally would, putting a 2 here and a 6 here with a plus in both places. So the second way is how I will factor most of the problems that are coming up. If you find it easier to make a substitution, as I did on the problem on the left, feel free to do that. So let's move on. Let's let the next example be x to the 22nd plus 6x to the 11th minus 7. Notice it does fit the pattern of the previous one, where the exponent that is first right here is double this exponent right here, and notice the variable doesn't even exist in the third term. So I'm going to set up my two sets of parentheses. And I have x to the 11th times x to the 11th. And it is now the same type of problem that we've done before. I look at my 7. 7 is 7 times 1, so I'm popping those in. I know one sign is plus and one is minus because I have a negative 7. So I'm going to put a plus on the 7 and a minus on the 1 so that I'll get that 6x to the 11th in the middle. I do always peek to see if there's anything else that I could do, because we have the sum and difference of cubes or the difference of two squares as strategies we need to consider. But x to the 11th is neither a perfect square nor a perfect cube, so there isn't anything else I can do to factor this one using the strategies that we've talked about. So we would consider it done. Let's do the next one. It is x to the 6th minus 11x to the 3rd plus 24. Do you see that it has that same pattern for the exponents? I have an x to the 6th and then an x to the 3rd and no variable at all in the last term. So I'm going to set up my parentheses, and I'll have an x to the 3rd times an x to the 3rd that will give me that x to the 6th. 24 is 1 times 24, or 2 times 12, or 3 times 8, or 4 times 6. So I like that 3 and 8 as a possibility for getting that negative 11 in the middle. I pop the 3 and the 8 in. Let's see. The signs both need to be negative. And we have it partially factored. This time, there's more that we can do. Do you see it? Do you see right here? we have a difference of 2 cubes. The first binomial has a perfect cube minus, and then we have 3, which is not a perfect cube. So that one's finished. But with this second one, we need to continue. So this is good practice, factoring the difference of 2 cubes. Remember, it's a binomial times a trinomial. The signs are the same, opposite, always positive. And with an x cubed and an 8, the x is being cubed and the 2 is being cubed. And now I roll out my pattern for the trinomial. So I take the that first term of x and square it. I multiply the 2 and the x together and write it in the middle. And then I have 2 squared, which is 4 for my third term. Each of these factors is prime with respect to the integers. So this one's done. Let's take a look at a problem now that is not a polynomial. I told you we would get to some of those. So here it is. It is x to the 2/5 plus 8x to the 1/5 minus 20. And it is certainly not a polynomial because we have exponents that are fractions, the 2/5 and the 1/5. But do you see it has the same kind of pattern? It is, again, quadratic in form. Let me just show you how you could write it. Again, if you prefer to make a substitution or just want to see why it's quadratic in form, we have x to the 1/5 squared. We have an x to the 1/5 in the second term, and the last term doesn't have a variable at all. Do you see that it's quadratic in form now? X to the 1/5 squared, x to the 1/5, and technically that's raised to the first power, and then we don't have a variable at all. So it's quadratic in x to the 1/5 power. But I don't need to make the substitution. Let's just set up our parentheses. And I'll have an x to the 1/5 times x to the 1/5. 20, let's see, 1 times 20, 2 times 10, or 4 times 5. I like 2 and 10 as the possibilities to give me that 8 in the middle. As long as I put a plus on the 10 and a minus on the 2, I will get that positive 8 in the middle. And this one is complete. I can't factor either of those two expressions any further. Let's do another one. Also not a polynomial. So our next example will look like this. X to the negative 2 minus 2x to the negative 1 minus 15. Notice it's not a polynomial because we have negative exponents, but we can still factor it using our regular strategies. We see that pattern with the exponents again. We have an x to the negative 2, and then an x to the negative 1, and then we don't have any variables at all. So I'm just going to set up my parentheses, and I will have an x to the negative 1 and an x to the negative 1 in the first spot. I factor it just like I would if it were a trinomial. The 15, I like 3 and 5, so I'm going to put the 3 and the 5 in. I need a negative 2 in the middle, so I make sure I put a negative on the 5 and a positive on the 3. And this one is complete. I can't factor it any further. Now this next one will be different still, but I want you to see that even though we have decimals in the exponents, the strategy that we use will be the same as we used in the other problems. So it will be x to the 9.2 power plus 12x to the 5.1 power plus 36x. And always when we factor, we look for our greatest common factor first. I hope you see it's an x to the first power. I'm going to put a 1 there for emphasis so that we can figure out the exponents in the parentheses. Remember, we subtract those exponents. So it will be x to the 9.2 minus 1 is 8.2 plus 12x to the 4.1 when you subtract those exponents plus 36. Do you see this fits the same kind of pattern as the other problems that we've done? The 8.2 is double the 4.1. So we can factor it the same way we did the previous few. We're setting up our parentheses. And in the first spot, I will have x to the 4.1 power. And for my last term, I have to split up 36, but it's not too bad since I need that 12 in the middle. So I'm going to use a 6 and a 6 and a plus on both. Do you see that those two factors are the same? Because they're identical, I'm going to write it in a better way. Let's write that as x times x to the 4.1 plus 6 squared. That's a better way to present that answer. And this one is factored completely. Let's go to the next one. Let's look at this next problem. We're going to factor completely 7x to the 18th minus 2x to the 8th minus 5x to the negative 2. And if you're feeling ambitious, go ahead and stop the video and try it on your own. There is actually nothing new in this problem. It's just going to be putting together the variety of strategies that we've seen. So, do you see the common factor of x to the negative 2? Let's take that out. That means we're left with 7x to the 20th minus 2x to the 10th minus 5. And remember those exponents. That 20 came from 18 minus negative 2, and the 10 came from 8 minus negative 2. Now our trinomial fits the pattern that we've been talking about. The exponent of 20 is double the exponent of 10, and we don't have a variable at all on the third term. So I'm just going to set up my parentheses and get ready to factor that trinomial. So I split up the x to the 20th into x to the 10th times x to the 10th. But notice the coefficient is not 1. So I need to make sure I have a 7x to the 10th times x to the 10th. And you can go to the side or to scratch paper and do your figuring for your trinomial. If you use trial and error or some other strategy, go figure it out there. I hope you can see that we're going to need a 5 here and a 1 here. And let's see, we need a negative 2 in the middle, so we need the 7 to be a negative and the 5 to be a positive. So if you were just foiling this out, you would have, not with that. You would multiply these two together and you would have negative 7x to the 10th. And multiply these two together and you'd have positive 5x to the 10th, which gives us negative 2x to the 10th. So let's continue. And if you're thinking, continue, that's as far as I got. Did you forget to look to see if you could factor further? Do you see that this binomial right here is factorable? X to the 10th is a perfect square because its exponent is even. 1 is a perfect square, so we need to factor further. I'm bringing down my x to the negative 2. I'm bringing down my 7x to the 10th plus 5. And now I'm going to factor into conjugates. My x to the 10th gets broken up into x to the 5th and x to the 5th. My 1 gets broken up into 1 and 1. I make sure I have 1 plus and 1 minus. Now, x to the 5th is not a perfect square, nor is it a perfect cube, so I can't continue factoring using our basic strategies, or the strategies that we've been talking about. So this one is complete. So notice how nice this one was. We had a common factor first, then we used our trinomial factoring strategies, and then we used the difference of two squares. Let's factor another one. Let's put it down here. I'll let it be 9x to the negative 100th plus 10x to the negative 97th plus x to the negative 94th. Sometimes I get tired of the same old exponents. I thought I'd throw these in for fun. When we jump in, do you see that common factor of x to the negative 100th power? Remember, it's the smallest exponent you see. Sometimes people aren't careful with this one or aren't sure what to factor out. But negative 100 is smaller than negative 94, so that's our common factor. And then I'm left with 9 plus 10x to the negative 97 minus negative 100 is a positive 3. Plus x to the negative 94 minus negative 100 is 6. Now, there is nothing wrong with factoring it in that order, but I don't like it that way, so I'm just going to take a step to rearrange it. I'd prefer the trinomial to look like this: x to the 6th plus 10x cubed plus 9. Now, that was unnecessary, but I prefer it, so I'm going to do that. Now, let's continue to factor. We have that same pattern again. So I'm setting up my two sets of parentheses. X to the 6th gets broken up into x cubed and x cubed. 9 will get broken up into 9 times 1 because I need that 10 in the middle. So I'm going to put a plus on both. Again, I look to see if there's anything I can do to continue. X cubed is a perfect cube, but 9 is not. So there isn't anything else I can do on this factor. But how about this second binomial right here, the x cubed plus 1? Do you recognize it as the sum of two cubes? So we can continue. Let's bring down our x to the negative 100. We'll bring down the x cubed plus 9. And I'm setting up my parentheses for the binomial and the trinomial. X cubed plus 1 is x to the 3rd plus 1 to the 3rd. So I'm going to have x plus 1 as my first factor in factoring that sum of two cubes. And let's see, I will have x squared minus the product of 1 and x in the middle plus 1 squared. Are you finding that easier to roll out that pattern? If you still don't have it down, you need more practice with that sum and difference of cubes. You might go back to the Beyond the Basics Part 3 if you still haven't practiced that one enough. But now when I'm looking at my last line, all of those factors are factored as far as we can. And this one's finished. Let's do one last problem. So here it is. It will be x to the 7 halves minus 7x to the 3 halves minus 18x to the negative 1 half. I thought we'd put some entertaining exponents in there. Notice that their common factor, x to the negative 1 half. So we're taking that out. And in our parentheses, we'll have x to the, I'm going over here to the scratch paper so you can see where we're coming up with the exponents. 7/2 minus -1/2. That's 7/2 plus 1/2. That's 8/2, and that is 4. So we have x to the 4th power. Similarly, we would have minus 7x to the 2nd power minus 18. And let's continue. We have the same kind of pattern we've been working with. So we have an x squared and an x squared. We have an 18 to break up. I'm going to make it be a 2 and a 9. Let's see, I need a 7 in the middle, a -7 in the middle. So I'm going to put a negative on the 9 and a positive on the 2. And do you see that we're not quite finished? Right here we have the difference of two squares. So keep going. X to the -1/2 times x squared plus 2 times x plus 3 times x minus 3, because we know that the difference of two squares factors into conjugates. So this one is factored as far as we can factor it with respect to the integers. I hope you enjoy factoring some problems beyond the basics.